y'all doing? Sleepy. I am sleepy, but that's going to be my usual answer. Sleepy or hungry. Also thirsty. Stay hydrated. All right. Today, we're going to start chapter 1, which is very much the introduction of the course. Scientific method, going into things like units and measurement and math and things like that. Before we get into that, first, everyone should at this point be added to the Brightspace page. I've submitted claims for all the students who told me they weren't in. I double checked every single possible list I had. Now, if I missed something, if you still don't have access to the Brightspace course, please let me know. I do apologize for the process, but I will make sure everyone gets in there. So, and if you sent me an email on Monday already and you still can't access, please send me another one because I submitted every email I got, and I'm going to need another reminder if that still didn't get you in. So please let me know if you still aren't. Before we get started, does anyone have any questions at all today? All right. I'll point out again, just in case people have Wednesday labs, there is not any lab this week. That includes today. Labs will begin next week. What I'm going to do first, since we're starting chapter 1. Where's my cursor? Oh, please. I'll point out where on Brightspace you'll be able to get the slides that I use. First of all, again, if you're still not able to access this, please let me know. On Monday, we kind of looked over the intro tab, which contains the syllabus, formula sheet, and the slides that I used on Monday. You scroll down. As chapters get added to the Brightspace page, each specific chapter will be noted based on the numbering of the textbook the course is based on. The tab itself lists the homework questions that you should be able to answer by the end of a chapter. You don't need to do them all immediately. It's like the questions you should be able to answer by the time I'm done teaching a particular chapter. Tab also contains a document copy of the homework and also the slides that I present. So you can access them here if you'd like to follow along. I've had plenty of students print them out and write all over them, whatever your preferred tactic is. If you do like to follow along, I will just note that sometimes the version here might differ very slightly from what I present, if for no other reason than I tweak my presentation as a week goes on. We usually cover about a chapter a week, and sometimes after one lecture I might think of a better way to write something, or I might add in a different example. So sometimes there'll be slight differences, and I'll try to upload the most up-to-date copies as those get made. But that is where those can be found. And for today, we will be beginning at the beginning, chapter 1 of this course. Focus for today is going to be talking about what physics is and the scientific method. Once again, before we get started with that, any questions, concerns, etc.? All right. Now, I'm very biased when I say this, but I think physics is very important. I think of physics as being a very fundamental, very foundational science, because again, in my biased opinion, physics is one of the most sciencey sciences, and we try to use it, well, I try to use it to explain everything in the universe. I can make any observation of something happening around me, and I can try to use physics to summarize why that was, or hypothesize about why that was. And since physics is very sciencey, we have to use the scientific method to be able to properly utilize science, go through the steps, and make sure we are doing good, data-driven science. So for today, we're going to go over the scientific method and talk a bit about what science is and how we should approach the subject of performing really any type of science. Now, when I say physics is very foundational, I like to visualize most of the things that humans can study or specialize in on sort of a line something like this. A line that goes from objective on this side to subjective on this side. And the more objective something is, the less room for interpretation there is when you're studying it. Numbers, again, in my opinion, tend to be very objective because 5 is 5. There's not really any interpretation about how much of something there is if there's 5 of it, you know? Numbers, I feel, are the most objective thing that you can study. So pure math, I put all the way over here on very objective, probably the most objective. No room for interpretation, and that makes it a hard discipline. Not necessarily hard in terms of difficulty, but hard in terms of rigidity. If you look up hard science, that means that there's not much room for interpretation in those sorts of disciplines, as opposed to, say, a soft science like psychology or sociology, which are sciences. You still employ the scientific method when you're studying those things, but these tend to be more subjective because they involve human perception, humans' emotions, interpretations, and things like that. So hard to soft is really just following along from objective to subjective. So physics, being on this end, the objective end, there's not always a lot of room for interpretation in the data that we collect, but there is still some interpretation required, and that's why it's a little less objective than pure math. We still have to interpret the numbers for meaning. That's really what the entire reason that we have numbers in physics is. We are interpreting them for meaning about what the universe is doing around us. And so it's a fairly objective discipline, but there is still interpretation. Physics requires human interpretation of data. Data is the most objective thing. Data is as close to truth, actual fact as we can possibly have. And the more interpretation you do of that data, the more subjective a discipline tends to get. So on this line, I kind of take a discipline and rate what applies that discipline a little further to the right. So I like to think of as chemistry as applied physics. What one does in chemistry, in my opinion, again, I'm biased towards the physics side, is that chemists apply physics to very specific things like chemical interactions and elemental science. And then biologists apply chemistry, chemical reactions, to what goes on inside of a biological organism. Psychologists apply biology to what goes on inside of brains. Sociologists apply psychology to what happens when a bunch of different people are all interacting with each other. Economists, language is hard, study what happens as societies develop money, and eventually you get all the way down to the most subjective things you can study, which include art and everything that involves nothing but interpretation and emotions. So someone could say math and art are opposites, but I wouldn't. I think that they're both important, not necessarily opposed to each other. They're just objective versus subjective. This class is going to focus mostly on the objective part, because we are again trying to interpret the data to draw as best an objective conclusion about what's happening around us as possible. And to do that, humans have invented the scientific method, the list of steps that we take to try to be as objective as possible when performing science, to be as sciencey as we can in our observations and in our work. And since physics is, again, my opinion, one of the most sciencey sciences in terms of objectivity, we need to look at those steps to make sure we can employ them, in our work. So, is anyone unfamiliar with the scientific method? Just want to check real quick. All right, just checking. I was planning on this part being mostly review. I've got the steps of the method listed here. The way that I write them out, there is 8 steps. We're just going to quickly go over them to refresh on what those steps are and talk about how we're going to be using them in this class. And really, how you guys use them all the time, regardless of whether or not you're trying to be scientific. Because like this method is kind of based on how humans inquire and answer things. So even if don't think of yourself as a scientist, you still do this sort of thing all the time. The steps of the scientific method, the steps to do good science, are first, you must make an observation and ask a question about why that thing you observed happened. So step 1, summarized to one word, would be observation, in my opinion. And as I kind of hinted at on Monday, humans are pretty good at doing that. You've been observing things happen around you for your entire life, correct? Whatever senses you have or are particularly strong in, you use it to make observations about the world around you. For example, just kind of an observation I'm going to refer back to constantly today, you can observe something fall. You see that it started here, you can observe it accelerate down towards the desk, towards my other hand. And humans made loads of observations of that happening over the millennia we've been on this planet, and they started to question, why does that happen? You know, what can we glean about the source of the falling phenomenon? How can we predict and calculate and take advantage of that fact, or possibly prevent it if you don't want to fall off of something? So any possible observation of the world around you is an observation. And then you usually ask a question about why that sort of thing happened. Why did it fall? Why is the floor of my dorm so cold? Why did that thing shock me? That's all the first steps of science. And again, humans are pretty good about that. We're pretty inquisitive overall. The next step is then performing research, which is to say, you look up if someone's already answered your question. Step 1 was asking a question. Step 2 was seeing if an answer already exists, which we're also pretty good at because most of us carry web-enabled things that allow us to literally look up the answers to most questions we can think of. So when you Google something, congratulations, you are engaging in the scientific method. You are researchers. That's really all it is. Now, if you find an answer to your question, you're kind of done. It just caps itself at step 2, and you've got the answer to your question. If there isn't an answer, that's when you have to move on to step 3. And step 3 is, why do you think that happened? You form a hypothesis about your observation. And hypothesis is really just the fancy scientific word for an idea. Every hypothesis is just a human-conceived idea trying to explain why something happened. Every hypothesis is just an idea. And again, you form a hypothesis every time you try to explain something. And they don't have to be good all the time, necessarily. Every idea, every attempted explanation is a hypothesis, even bad ones. For example, I'm going to refer back to the falling observation a lot today for an example. Let's say that, if we go back to before humans had scientific notions of gravity, we would still observe things falling, and maybe one day an early human tried to figure out an explanation for why things fall. So they watched an apple fall out of a tree. They observed apple fall out of a tree. They asked the question, why did that happen? Research, before books would probably just consist of asking all your friends if they know why it happened. And then if none of them have an answer, you try to answer it yourself. So I saw that apple fall out of the tree. I noticed that a bird flew overhead as it happened. So I hypothesize that apples are afraid of birds, and the apple fell out of the tree to run away from the bird. Is that a good hypothesis, based on how we know the universe works these days? No, but it's a hypothesis. This hypothetical person is attempting to engage in the scientific method. They came up with some idea for what happened. And once you have your hypothesis, whether it's a good one or a bad one, you then have to test it. Because everyone can come up with ideas, But that idea, that hypothesis can only move forward if you move forward in the method and actually try to prove it. So step 4 is where you try to prove it. You perform an experiment and collect data to try to validate your hypothesis. And step 4 is the most important part, as it turns out. At least the most important part for us in this particular class. Because step 4, the experiment, is where you record data. To do a good experiment, you need to have data about what's happening before you begin, the initial conditions, what happens as the experiment goes on, and then where everything ended up, what state and location it's in at the end. You need all of that data from start to finish to have a good experiment. Initial, middle, and final conditions. And the data is the closest thing that we can get to fact and truth when studying science, because most observations and human ideas are skewed by human perception. If a human came up with an idea, it's inherently flawed, because we don't know everything. The ideas we come up with are based in our observations and our own biases. So the data itself is as objective as we can get here. It's as close to truth as we can really surmise. And the data is basically just math. It's just the numbers. Again, it's the most objective thing you can have. So to have a good experiment, you need to record a lot of data, as much data as you can get. To paraphrase Adam Savage, I'm going to mention Mythbusters a lot when I teach. The only difference between science and messing around is you got to write everything down. Record your data. And we have to use the data to do math, and we use the math to try to verify our hypothesis. So you take the data from step 4, you use it to try to see if it verifies your hypothesis or not. So let's devise an experiment for that idea that apples are afraid of birds. Let's say that you find an apple orchard and you observe throughout the day whether or not apples start falling as birds fly overhead. So your initial conditions would be, I'm watching this particular tree, there's 10 apples hanging from it, and throughout this day I'm going to note when birds fly overhead and see how that compares to when apples fall. So the initial conditions, apples are in tree. Final conditions, how many are on the ground? Did they fall as birds fly overhead? So someone could perform that experiment. Over the course of the day, maybe 1 or 2 apples would fall, and as they fall, you look up, no bird. And they would write that down. And then at the end of the day, they'd look at the data and they'd say that there does not appear to be any mathematical correlation between the presence of a bird and the falling of an apple. So the data has disproved the hypothesis, and you have to form a better one. It's only by proving that, it's only by going through that process that we can figure out apples aren't afraid of birds, so we go back to the drawing board. Hypotheses are just ideas. You have a ton of them. And again, humans make mistakes all the time, so a ton of hypotheses are just wrong or bad, and you only get to the good ones by experimenting and comparing your idea to the data. Eventually, though, you get a good hypothesis, you do another experiment, and the data actually corroborates it. The data seems to validate your hypothesis. Your idea is working. And then you do the experiment again, because you always have to do it more than once. Do the experiment again, it keeps working, your hypothesis keeps seeming to work out. What do you do then? You gotta tell people. You share your hypothesis with other people, and they test it too, because other scientists have to be able to replicate your results. And if a bunch of scientists test your hypothesis, do your same experiment, do slight variations of your experiment, and they keep finding the hypothesis to be true, if things keep working out as you described them in your hypothesis, and people agree with you, that hypothesis evolves Pokemon style into a theory. And so that is step 6 is share, which is also very easy. Technically, you are sharing your data whenever you post anything online. So again, the internet is pretty good at facilitating science. 7 is the theory stage. A bunch of people test the shared data, shared hypothesis. If a bunch of people test it and find that it works out, then it becomes a theory. Then, if after about a century or so, a bunch of people keep testing it, keep finding it to be true, keep thinking of it as good and useful and true, that's when it evolves from theory to law. And so that is where all the laws of physics came from. And that's the scientific method. And that's how you too can eventually end up in the history books as contributing to the laws of physics. So to have a hypothesis, and a bunch of people have to agree with it. Questions so far? All right. Now, how does this relate to this class? Primary thing that we need to use this for is to make sure that we are basing our math and our observations on data. Physics is data-driven. We want to make sure that the conclusions we draw about the universe are as close to fact as we can get. And for that reason, we base all of our conclusions, all of our math, directly on data that we can measure. So the measurement is going to be very important, because measuring is how we acquire data about the universe. So, on Friday, we're going to talk about measurement units and the algebra we're going to be using, how we take data and what we're going to be doing with it. Even our concepts in this class are going to still be data focused, because physicists do like to use math as a language. I look at a formula and I use it to draw a narrative, draw comparisons between all of the things present in that formula. So data is good. We like data. We record a lot of data. We base even our concepts and our definitions on data. So data is good. Data is as close to true observation as we can get. But there's another point I want to make about science and about physics that I want to talk about here at the ground level before we move forward, before we get any further into the class. And to make this point, I'm going to go back to the method, but I'm going to go backwards and start at the end and go back to the beginning. The last step in the method is law. And this is where, again, the laws of physics come from. The term law of physics just means that physicists agree this statement is the way we understand things to work. But if we go backwards, every law of physics was previously, bless you, a theory of physics. And every theory of physics, we go even further back, began life as a hypothesis of physics. And hypotheses are just ideas that a guy came up with. It's just an attempt at explaining what you saw happen that popped into your head one day. Every law of physics is just an idea someone had. The laws of physics are human constructs. We invented them to try to explain the universe around us. The term laws of physics does not refer to the immutable truths of the universe. The term laws of physics refers to mankind's current best scientific attempts to explain the universe. We wrote the laws of physics. We didn't write the universe. The universe exists, the universe does things. And the laws of physics are our best explanation as to why it does those things. Gravity isn't real. Gravity is a word that we made up to describe this. Gravity is a human concept used to explain this phenomenon and several other related phenomena. Laws of physics aren't real. The laws of physics are the way we currently understand the universe. And because they started here as an idea in a human brain, they are inherently flawed. Because humans are flawed, right? Our meat calculators get things wrong all the time. And every hypothesis started in some guy's meat calculator. That means all the laws of physics are flawed. They can be wrong, and over time they need to be improved. I'm bringing this up to try to point out that it's okay to be wrong in this class. It's okay to make mistakes. It's a part of the process. You only get to the good science by making the mistake, having a bad hypothesis, doing the experiment to disprove it, and then moving on to a better hypothesis, to a better experiment. That's a part of the process. Being wrong is a part of the process. And what's important about being wrong is admitting it and going back to the drawing board and fixing it. All of science is this process, continually being wrong until you eventually get it right. So you will you will be wrong sometimes in this class. You will make mistakes in lecture, on your homework, in your labs, on your tests, and that is fine. Physics is hard. You're gonna mess up, that's fine. I messed up loads of times. There are still parts of my own discipline that I hate doing. And that's okay. It's okay to make mistakes. I'm going to help you fix them. I want to now tell you a story about what happens when scientists don't want to admit they've made a mistake. Who's ready for the tale of planet Vulcan? Any Star Trek fans in the audience? So, I trust that most of you are familiar with the name Isaac Newton. Pretty important guy to Western European science. Got very famous for his equations and his observations about gravity and force and motion overall. In fact, the first formulas that we're going to go over starting in chapter 2 are going to be Newton's laws of motion. Pretty important. Now, Newton was not perfect. And in fact, Newton wasn't even the first person to ever talk about gravity because, again, people have been noticing this for all of human history. So Newton didn't discover gravity, because again, gravity isn't real. Gravity is an explanation of the falling phenomenon. But Newton is the European that got famous for it. And his equations are very good. It's why we still study them. It's why they're going to be some of the first things we talk about. But Newton is a very flawed human. And that means that inherently his work is flawed. Because there's certain data that Newton couldn't have had centuries ago. But at the time, Newton's work was so good. Newton's work on gravity and motion allowed us to track, to predict the motion of pretty much every object that humans could physically measure. You know, on planet Earth, every object that you can perceive using your senses and measuring equipment, Newton's formulas were very good at predicting the motion of. As long as you know an object's mass, the forces acting on it, where it currently is, Newton's math is perfect for figuring out where it is now, where it is going to go, and at what speed. Newton's work is great, that's why we still use it. And for centuries, Newton's laws were the best tool we had for talking about motion on planet Earth and even in the solar system as a whole. Because Newton's formulas weren't just good for terrestrial math, it was also good for predicting where planets would be in the night sky. Namely the planets within our own solar system, because once you leave the solar system, things are too far away. But with early astronomers, well, 1500s European astronomers, were able to predict the motion of planets in the solar system based on what we understood about gravity and motion, thanks to the work of Newton. Like they could see where Jupiter was on one night, and then based on observations about its assumed distance from the sun, its mass, how gravity works, they could figure out where it would be the next and they'd be right. Next night, and they'd be correct. And that worked for every planet within our solar system. It even helped us to conclude that Pluto existed. We didn't know that Pluto existed until the last century because our telescopes weren't able to perceive it. It's physically just too dark unless you are using dark night telescopes in the middle of nowhere where there's no light pollution. I've been to the lab where Pluto was discovered. physically, the guy who found it had to be in the middle of nowhere in absolute darkness to get enough light visible to see it. Literally stumbling around in the dark. He had to pad his entire lab to not knock himself out on his metal equipment. Which is another good reason why, as time goes on, we get better data to help our assumptions. Like, 5 centuries ago, we didn't have the data to know Pluto existed. A century ago, we could finally get that data. Now Newton's work again, very good. Help us track all of these planets, except one. Can you guess which planet Newton's laws could not predict the orbit of? Yes?
The sun?
That'd be an interesting twist, but sun is not a planet. But I mean, that would be a fun twist, but no. It wasn't the sun. I will say it is a planet. I said what planet, so which one? I will say though, actually, you did kind of, the sun is involved, and I suppose Newton's laws would be pretty bad at predicting its motion for the reason I'm going to explain. So you're not wrong. You answered a different question. That would be another good twist, but also not the one I'm thinking of. No, actually. Those two are, those are probably the easiest to track because they're the most visible. That one and Venus. Yeah, the rings do make Saturn's visible a bit easier.
Yeah.
It's okay, those are the big ones. The big ones tend to be easier to see. Who's next? Not the moon. Moon's actually the easiest thing to see. I think you were next. What's your hand up?
Mars.
You're getting closer. I think you were next. Mercury, the other one that starts in M. Mercury! This pesky little thing. Very fast and very small and very close to the sun. For some reason, Newton's math could not quite nail down Mercury's position. It was always close, but it was never exactly where it was supposed to be. And that bugged people, because Newton's laws are supposed to be great. We've used them for hundreds of years. There's not supposed to be anything wrong with them. But they weren't quite working to predict Mercury's orbit. And that's kind of a problem, because if they don't quite work here, where else are they not quite working? Newton's laws can't be flawed. We need them. Now, at this point, if we were properly using the scientific method and doing good science, this would be the point where the data no longer matches the hypothesis. And at that point, we need to be able to admit something's not working and figure out a better hypothesis, figure out what's actually going on here. But this is the point where physicists messed up. This is the point where they didn't want to admit they were wrong. Because Newton's laws are great. We don't want to have to replace them. We don't want them to be wrong. They're our best tool. We spent a lot of money on this fancy thing. I don't want to get rid of it. So rather than form a new hypothesis, they kind of tweaked the data into their favor. Someone did a bunch of hypothetical calculations, not based on real data. They figured that they formed a hypothesis, but one they couldn't test super well. They formed the hypothesis that what if there's an extra secret mystery planet in the solar system whose gravity is affecting Mercury's orbit? Because that's what gravity does. As two objects get near each other, the force between them affects their motion. And so someone did a bunch of math and predicted, hypothesized, that if there was this extra mystery planet somewhere in our solar system, it could be affecting Mercury's orbit in such a way to cause the results we were seeing. Now, we didn't have any data that this planet existed. We'd never seen it. But they just kind of started assuming it had to be there, because it was the only way that Newton's laws could predict Mercury's orbit. And so again, they didn't have data that it existed. They took their existing data and kind of forced a new hypothesis into it to make it work. They didn't want to admit they were wrong. And of course we've never seen this mystery planet because it's always on the wrong side of the sun. The sun's always blocking it. That's why we've never seen it. Which literally doesn't make any sense, because if it's this close to the sun, it should be moving fast enough to eventually come around the other side of it and eventually enter our sight lines. So this idea was very poorly conceived from the start. But they didn't want to admit they were wrong. They didn't want to admit Newton's laws could have flaws in them. So they just assumed this planet was real. And in keeping with the roughly Roman theme of most of our solar system, they called it Planet Vulcan, the Roman counterpart to Hephaestus. And, again, no evidence that this planet was real. They assumed it was, and for, I believe, centuries plural, actually put it on maps. So, Vulcan's not really real, so Spock's homeless, sadly. But there were maps that said it existed, and kind of as an homage to this, Gene Roddenberry, creator of Star Trek, named his planet Vulcan after this whole catastrophe. But as science advanced, we got better tools, we got better data, we were eventually able to see what was going on the opposite side of the sun, and yeah, there is no planet Vulcan. There is no extra mystery planet. That meant, back to the drawing board. Newton's laws were wrong. They were not accurately predicting the motion of Mercury. That meant that they were flawed, and we had to come up with a better hypothesis. So, I think for at least a century, we weren't willing to admit our mistake, and we just fabricated planet Vulcan to cover the problem. So, if those professional scientists are able to make a centuries-long mistake, you guys are able to make one miscalculation. Fair deal? All right. Now, to kind of briefly summarize what's actually happening here. Again, Newton didn't have the data, didn't have the tools to measure what was actually happening here. But within the last century, Einstein came along using new tools and new data and gave us the concept of general relativity. The idea that space and time are relative to where you are in the universe, the mass of nearby objects, and how fast you're moving. The flow of space and time are relative depending on those three things, and that's why it's called relativity. Turns out timey-wimey and spacey-wacey are real things. Time gets timey-wimey if you happen to be near a supermassive object like the sun, whose gravity is affecting time on planet Mercury. This isn't quite on this course's syllabus. You're not going to have to do any math about this, but I do find it very interesting and I love talking about it. Basically, to quickly summarize, the sun's gravity is so strong, it's creating a time well, causing time dilation, and Mercury's trapped in it. 1 second on Earth isn't quite the same as 1 second on Mercury. And so, of course, Newton's tools couldn't have accounted for that. So, of course, Newton's laws can't account for that. But once you factor in that time dilation, suddenly Mercury's orbit makes sense. 1 second here is not the same as 1 second there. If you account for that, you can chart Mercury's orbit. So, Einstein, relativity, fixed the problem with Newton's laws, and now relativity is what we use to try to track the motion of very fast, very massive objects through space. And even then, there's still flaws with relativity that quantum mechanics is attempting to try to explain better. So science, physics, it's constantly evolving. All of the old laws are flawed because they're human inventions and we have to keep revising and replacing them. So I am going to teach you our best current laws and explanations for how the universe works. As time goes on, they will be improved, and as time goes on, you will improve in your ability to understand the universe, and it is okay to make mistakes. Sound fair? All right. again, I just like talking about this. Feel free to get me distracted on space at any given time. Big supermassive objects like the sun, their gravity slows down time. You might have seen this in Interstellar. That's kind of what the whole movie is about. Traveling through to those big supermassive planets causes the time rate to change, which is why at one point in the movie, 5 minutes for the main character was like 40 years back on Earth. That's an extremely extreme example. The difference in time between the Earth and Mercury is like 2%. It's not that extreme, it's just enough to be a problem. But gravity affects space-time. And also it turns out speed does as well. The faster you are moving, the slower time feels for you in comparison to the rest of the universe. That does come up in Interstellar, but it also comes up in light year. Because the ship goes too fast and he ends up in the future. Because time was slower for him than it was for everyone else. A minute on his ship was 10 years for everyone else. This is the hand-wavy explanation for why the Flash can time travel. But this method would work to get you to the future, but it wouldn't work to get you to the past. So there's still no good explanation for how the Flash ends up in the past. But he could end up in the future if you move fast enough. So, questions? Okay, now let's see. Let's bring this back a bit and summarize how we're going to be using all of this information for this class. 1, it's okay to be wrong. You're going to make mistakes, and that's okay. 2, the laws of physics are not facts, because humans invented the laws of physics. The closest thing to fact that we have in this class is data, and that's why we have to record data, and that's why we have to do math. So, in lab, we're going to be doing experiments, collecting data, doing math based on the data, and drawing conclusions based on the data. In class, I'm going to give you data about a hypothetical situation, or even possibly a real one, and we'll use it to use math and figure out what's happening, make assumptions about what would happen next in that scenario. I'm also going to point out that you want as much data as possible, and that includes the initial conditions of your experiment. You need to know where everything starts. Bless you. If you have initial conditions, like you record where something is and what it's doing before something starts, and then also what happens as it goes to where it ends up. That's called an operational science. In physics, we want to try to do operational science that involves knowing the initial conditions, the middle conditions, and the final conditions. If you know the initial conditions, you can perform an operational science and you can repeat that experiment to get good data. So this data for this golf ball falling, initial conditions are it's here, and we can perform an experiment to observe it fall down to here. You know where it started and where it wound up. This operational science is different to a historical science. If you're performing historical science, you don't know for absolute certain the initial conditions. You didn't have them written down at the time, and no one wrote them down for you. You just don't have them. So, lacking the initial conditions for this golf ball falling onto my table, let's say you walk into the room and the golf ball is just here. You didn't see it fall, and no one else was in the room to see it fall. It's just right here. And the goal of a historical scientist is to figure out how it got here without knowing precisely where it started. And the problem with that is, like, you can reasonably guess it started here and it fell straight down, but it also could have started anywhere else. I could have thrown it into this little socket on my desk from the hallway, and in which case it would not have begun here. It would have had a different velocity and it would have hit the desk at a different angle. Who knows what sort of effect that might have had. Furthermore, it could have just always been there. Like, for as long as I've been teaching here for 5 years, I was a student here starting in 2010, maybe as far as you guys know, that thing's been there for 15 years. That's the problem with historical science, you don't know. You don't have the initial data. In physics, we want operational science, we want those initial conditions as often as we can. If you don't have those initial conditions, all you can do is guess, and you really can never get out of the hypothesis stage because you don't have the data. You need the data from an experiment to be able to move from hypothesis to theory. Historical sciences can't really get out of the hypothesis stage, and historical sciences include, but are not limited to, archaeology, because we have fossilized bones in the ground, but we cannot guarantee everything about the organism they came from or what it was doing before it died. And meteorology, weather, is also a historical science, because the weather people don't know the location and velocity of every particle in the atmosphere, nor can they totally predict where they will all end up for that reason. And that's why the weather forecast is So, we like operational science, we like data, we like initial conditions. All of that to summarize is why we need to start doing math. And so on Friday, we're going to start doing math. Namely, and I'm just showing you this, I'm not going to begin a whole new thing right now at the end of class. First couple pieces of math we're going to begin are first talking about units and measurement, because to get data we have to measure things. We have to talk about the units that we measure things in, which will include the metric system. Sorry, perpetual Americans, but we're going to have to use metric in here. That includes metric prefixes and common metric units like newtons, grams, and meters, and we'll have to be able to convert those units back and forth from, say, feet to meters, and also use those metric units in equations to calculate new stuff. So Friday is going to be units, conversions, and algebra practice. Sound fair? Any questions before we break for the day? All right. Let me know if you need anything, especially and including if you're still not in the Bright Space course. If you have any questions, and please have one today. Stay warm and safe.